Hello and welcome to this, the second video of our clustering week, where we are going to look in depth at the method that we use for computing our clusterings, the thing called the k-means algorithm. The k-means algorithm is a very, turns out, simple way of solving a very difficult problem. And so we are going to look at it. We're going to basically, I will declare what it is, and then we will prove that it works. And in proving that it works, we will show why it is the way that it works. It's a very lovely and constructive proof. And really, who doesn't love a proof delivered via video? I know that that's personally what I spend all of my nights doing. Sitting down, watching videos of proofs. I've heard of Netflix, but I'm not sure why you'd want it. So what's our aim for today? Our aim is to take a set of data which consists of n points in p-dimensional space, x1 through to xn, and we want to somehow cluster them into k groups. Okay? How do we want to cluster them into k groups? Well, we want these clusters to be sort of as tight and distinct as possible so that 2 points in the same cluster should be closer or more similar in some sense than 2 points in different clusters. In particular, what do I mean by in some sense? I mean that they should be closer to their cluster center. Okay, and our cluster centers we are going to call Zj. Throughout all of this, I is the index of the observation and j is the index of the cluster. So we need to recall our question of how do we tell if a cluster is any good. And one way that we can do that is we can say that clustering is good is if we make the smallest possible error that we could make if we replace all of the data points by their corresponding cluster centers. Okay, that is if we find a set of Zs such that it minimizes this somewhat complicated cost function. Okay, the cost function c is given by the sum over all of the points of the smallest distance squared between that point and a cluster center. If we do this, then we can read off the cluster associated with the ith data point as the actual value of j dash that minimizes the squared distance. Okay, so by minimizing this, we can try and find our cluster centers, and a little bit of post-processing, okay, a little bit of just running through the data and finding the closest one will let us get our cluster assignments as well. So, what is an important thing to notice? Well, an important thing to notice is that this problem is really difficult. Okay? In technical terms, it's something called NP-hard, which basically means that there is no fast way of solving it. Okay? We cannot exactly minimize this function in any reasonable amount of time. However, it turns out there are many heuristic algorithms for solving this problem. And we're going to look at probably the most common one, which is an algorithm called k-means. It was proposed by Lloyd at some point in the distant past. Long enough ago that sometimes, I know that it's done by Lloyd because it's the option that you choose in R, but the algorithm has moved into ubiquity, which is very exciting. Okay, the nice thing about it is it's a fairly direct algorithm, and unlike most things, you can fit really all of the details that you need to implement this algorithm onto one slide. So here is the algorithm in one slide. Step one, we need to have an input, and our inputs are our data, which are our x's, and the number of clusters, k. And our output is going to be cluster centers as well as cluster labels, this j bracket I thing. So it is which cluster j the ith point is in. So there are essentially 2 steps to this algorithm. But before we can start these steps, we need to initialize. We need to start with somewhere. We need to start somewhere. And the best way to start somewhere is to just pick some points. So you choose k points uniformly across your set of points, and these are your initial cluster centers. We will, in the next video, reassess this choice a little bit, but for now, it's a decent place to start, and it's what Lloyd said to do, so let's do it. And then you do 2 things. And you repeat these 2 things until stuff stops changing. Okay, so the first thing you do is I have k cluster centers, Z1 to Zj, but I do not yet have cluster assignments. So I'm going to need those, and so I will compute them. So for each of my data points, find the cluster that it is in. Find the cluster center that is closest to the point. And there's a thing in bold here that says breaking ties consistently. What does that mean? Well, in the unlikely event that a point is equidistant from 2 cluster centers. Okay, so there are 2 possible values, or 3 possible values, multiple possible values that minimize that squared distance. Then the algorithm should always choose the same one. And this turns out to be extremely important for this algorithm to converge. Okay, the typical way that you would implement this is you would say, I will pick the smallest j that minimizes that squared distance. But once I've done that, I now have cluster assignments. And so I want to update my cluster centers. And I'm going to choose to update my cluster centers by the centroid, or the average, of each cluster. Okay, so you can see there that Zj is quite literally the average. That absolute value sign around the Cj is the number of points in the cluster. And the sum of them goes over all of the points that are in the jth cluster. And so this is the average point in the jth cluster at the moment. Okay, so this notation Cj, that is all points I, or all indices I, such that the cluster that xi is in is the jth cluster. And this is where the word k-means comes from, or the name of the algorithm k-means comes from, because we are using the mean of the cluster as its center. And there are k of them. That's where the k comes from. But now that we've done that, we've got a new set of cluster centers. And it will not necessarily be true that every point is assigned to the correct cluster with these new cluster centers. And so we have to go back to step 2.1 and check and recompute all of the cluster assignments to make sure that each point is still as close as it can be to its cluster center. If at this point nothing changes, we have found a minimum and we are done. Otherwise, we take our new clusters, we compute a new center, and then we repeat this over and over and over again. It's a very, very, very lovely and straightforward algorithm. I love it. It makes me so happy. So, it's not, however, completely obvious that this lovely and straightforward algorithm, and I say it's lovely and straightforward, and I will encourage you to try and program it up, because it really is a nice, warm, fuzzy feeling that you get. Again, I don't have Netflix. A nice, warm, and fuzzy feeling that you get when you just write this down and go, yeah, this is doing the right thing. I very clearly live alone. So what is the convergence of k-means? Well, it's not at all clear from just stating that algorithm that it's going to actually work. But it turns out it does. And we can prove, and we shall over the next couple of slides, prove that the k-means algorithm converges in the sense that it finds a local minimum of the objective function. Okay, remembering that that objective function can be written in two ways. It can either be written as the sum over all of the data of the smallest distance between the point xi and a cluster center, or it can be written as the sum over all of the clusters of the distance between each point in that cluster and the corresponding cluster center. So we can write it both ways. It's going to turn out that this second way of writing it is slightly nicer for the proof. And the second thing is that this algorithm terminates in a finite number of steps. So unlike if you've ever tried to program up something like Newton's method for finding the minimum of a function, in that case, you keep on going until you're close enough. Okay, you never actually get to the exact minimum in a finite number of steps. Here, we actually do. And it's going to turn out, and we'll talk about this in the next video, that that number of steps is not that big. It's a relatively small number of steps. So, we're going to do this in basically 2 steps. If we recall the algorithm, it only does 2 things. One of them is just bookkeeping. So step 2.1 is bookkeeping. We know that we want the point to be the label to be the one that is closest, that has the closest cluster center. So 2.1 is bookkeeping. The only thing that's weird here is 2.2. So we need to show that 2.2, that doing that step will never increase the objective function. And the second thing that we then need to show is that this actually terminates in a finite amount of time. So let's see if we can do this. Step 1, 2.1, step 2.2 does not increase the cost function. Okay, so first of all, it does not change the partition. Each point has already been associated with the label. The bookkeeping is done. So we can write this exactly as a function of these cluster centers, just like that. It is a smooth function, okay? If you squint and remember the definition of this sort of Euclidean squared distance, this thing is going to be quadratic in the z's. Okay? So it's a nice smooth function, and we can actually find its minimum by setting its gradient to 0. We're going to have a quick reminder of what a gradient is on the next couple of slides, but just trust me on that. Okay, it's like setting the derivative to 0. Okay, if we want to find the minimum of a univariate function, we set the derivative to 0. If we want to find the minimum of a multivariate function, we set the gradient. Okay, for each cluster center, we can actually write down what that gradient is. So the gradient with respect to the multivariable vector valued variable zj is just given there as twice the sum of the difference between xi and zj. That sum is over all of the xi's in cluster j. Okay, so that's where we're going to be. Let's just do a quick aside to make sure you remember what a gradient is. Okay, a gradient is basically a multivariate version of a derivative. Why does it need to be special? Well, if I've got a function of a bunch of variables, I can actually have a whole bunch of different derivatives. I can have the derivative with respect to the first variable, the second variable, the third variable, etc., etc., etc. And usually I actually need all of these. So I put them together in a vector. Okay, and that vector is called the gradient. So this upside down triangle thing is the letter nabla from an alphabet that honestly at this particular moment in time off the top of my head I cannot remember. But you do know how mathematicians love just raiding an alphabet just for fun. So nabla is the upside down triangle. And it is a vector, and the jth component of the vector is the partial derivative of f with respect to xj. So what's a partial derivative? This curly d thing? It means take the derivative with respect to xj as if all of the other variables were fixed. Okay, you just pretend they're constants and you formally take the derivative. Okay, on the last slide again, we wrote nabla sub zj to indicate that we were taking the gradient with respect to zj. So just to remind you about, maths, if we have a function fz, which is x minus z, the norm of x minus z squared, which is the sum of xj minus zj squared across all of the components, then we get the partial derivatives df dzj. Well, we don't really need any of the ones except for the jth one because they're all constant as far as this partial derivative is concerned. So we just get the derivative of xj minus zj squared, which is twice xj minus zj. And that's each component of the vector, and so we can put that all together to get the full vector as twice x minus z. And because of that, we got that the gradient with respect to zj of c was twice the sum, because we had one of these for each of the observations in the cluster, of xi minus zj. And if we want to find the minimum, we need to set that thing to 0. And then we can do some algebra. Okay, the zj doesn't depend on I. So you just get the number of things in a cluster. So that term appears in the sum cj, absolute value of cj times, and the other thing turns out to be the sum of the xi's, or equivalently zj is equal to the average of the xi's. So this means that step 2.2 is choosing the cluster centers that minimize the cost over all possible choices, which means that that step cannot possibly increase the cost function. It will either keep it the same, in which case we have terminated, or it will go down. Okay, so we have this sequence of numbers that are either staying the same or going down. And we can finish the proof with the technical bit at the end, which is to say that the algorithm actually finishes. So it's almost enough to say that step 2 will never increase the cost function, and that the cost function, being a sum of squares, is always non-negative, which means it cannot keep on decreasing forever and ever and ever. At some point it hits a floor, and it can never decrease. The only thing that can go wrong, is that there are multiple configurations, okay, multiple choices that you can make of the labeling step 2.1 that have, you can have multiple things of that. So what would basically happen is, let's say points 1 and 2, or point 1 is equally spaced between cluster 1 and cluster 2. Okay, if I run through my algorithm, I'm at the possible minimum. I did my assignment to cluster 1, I check, nothing changes, then I move back up to step 1.2, and then I assign it to cluster 2, then actually it's going to change again. I will find the minimum there, but then I might go back, and I will end up flipping, cycling through these things. Okay? You end up with a bunch of values that have the same cost. We do not want that. It's silly and inefficient, and the way that you prevent this is by making sure that when there are 2 possible values of the label, you break the tie consistently. You choose the same one every time. Okay? And this means that it will go down, and it cannot keep cycling between equal cost configurations, and it will eventually converge to a local minimum. And that ends our proof. Our first proof for STA 314.